Alright, so here's a nice little problem to illustrate the variational principle. Suppose we have a potential, so it's got an infinite wall at the origin, or at x equals 0, alright? So the wave function has to go to 0 beyond that point. But then it just has a linear, like a ramp, alright? So it's just a x multiplied by some constant we'll call k or kappa or whatever you want to call it. And so we have this trial wave function that we're going to be trying on this. And then we're going to try and find an upper bound for the ground state energy for this potential. So here's our trial wave function. It of course goes to 0 for past this infinite wall, right? It has to. We have a normalization constant a, which we need to find, and then a variational parameter is alpha here. So first what we're going to do is normalize this wave function. So we'll find a, and then we will we'll find the expectation values of the energy, so the kinetic and the potential energy, and then we will tweak the alpha, or basically find whatever alpha it is that gives us the minimum energy. So this will set an upper bound on the actual ground state energy for a potential like this. All right, so to start off, I'm going to take a different sheet on this, and we're just going to do some integrals because it just turns out that we'll need a few of these integrals. So why not just do them all right off the bat? Feel free to skip ahead if you don't want to just see a bunch of integration by parts, because that's all this is going to be. All right, so the first integral I will call I3, and that goes from 0 to infinity x cubed e to the minus 2 alpha x dx. All right, it might not be immediately obvious why we need this, but we will need it later on in the problem, so we might as well do it now. So I'm going to do integration by parts. Set u equal to x3, therefore du is equal to 3x squared. dv we set equal to e minus 2 alpha x dx, which sets v equal to e to the minus 2 alpha x divided by a minus 2 alpha, telling us that I3 is equal to uv minus v du, integral v du. So uv is x3 e to the minus 2 alpha x over minus 2 alpha. So this multiplied by this, and that's evaluated 0 to infinity. All right, and this term is going to be 0 because when we plug in infinity, this exponential will go to 0. When we plug in 0, this x cubed is going to go to 0. So we won't have to worry about that. All right, and then we minus v du. I'm going to bring out the minus sign from this denominator here and make a plus sign out front. So we're going to have a 3 from this and a 2 alpha from downstairs here. 0 to infinity, and then we have an x squared e to the minus 2 alpha x dx. All right, so we already showed how this goes to 0. So now we have another integral to do. So I'm going to have I3 here be equal to 3 over 2 alpha, and then I'll call this one here I2. You can see where this is going. Let's start again. We have I2 is equal to integral 0 to infinity of x squared this time, e to the minus 2 alpha x dx. I'm setting u equal to x squared this time. Du equals to 2x dx. The dv is going to be the e to the minus 2 alpha x dx, which makes v e to the minus 2 alpha x over minus 2 alpha. All right. So here we go again. We have I2 equal to uv, which is x squared e to the minus 2 alpha x over minus 2 alpha, again evaluated from 0 to infinity. And again, we still have the same thing that happened last time. At infinity, this goes to 0 because of the exponential here. At 0, it goes into 0 because of the x squared, so this is going to 0. Again, we have a minus sign here, which I'll bring out, so we'll make this a plus. We have a 2 and a 2 coming out. That will divide out to give us a 1 over alpha. And now we have integral 0 to infinity of x e to the minus 2 alpha x dx. All right, so now to sum up, we have I2 equal to 0, and then 1 over alpha multiplied by this one here, which I will call I1. All right, now we will do I1. I1 is equal to the integral from 0 to infinity of x e to the minus 2 alpha x dx. U we will set equal to x, du equal to dx, dv we set equal to e to the minus 2 alpha x dx, making v equal to e to the minus 2 alpha x divided by minus 2 alpha. All right. This means that our integral I1 is equal to uv, right? So x e to the minus 2 alpha x, excuse me, minus 2 alpha, again evaluated from 0 to infinity, and we still have an x here, so this again goes to 0. All right, and then we'll do our VDU, which is, again, bringing out a plus sign, 1 over 2 alpha, integral from 0 to infinity of e to the minus 2 alpha x dx. All right, and of course we're calling this I equals 0. So I1 is equal to 1 over 2 alpha I0. Now we solve for I0. It is equal to the integral from 0 to infinity e to the minus 2 alpha x dx. All right, which we can just do finally. Just e to the minus 2 alpha x over minus 2 alpha. That's a minus sign. Evaluated from 0 to infinity. Our infinity limit here will still go to 0 because we still have this exponential, but our when we go to 0, this is going to 1 upstairs. All right, and this minus sign here will cancel with the minus sign we get when we take our limits, and we just get a 1 over 2 alpha. Okay, I hope I did this right. Okay, so there's probably a nice formula you can look up somewhere in integration tables, which has this all done for you. Maybe I should look that up and put it in the video. I don't know. If I take a break, maybe I should. All right, so I0, let's just write a summary of what we found here. I0 is equal to 1 over 2 alpha. I1 is equal to 1 over 2 alpha multiplied by I0, we see right here, which is equal to 1 over 4 alpha squared. I2 is equal to 1 over alpha I1, which is equal to 1 over 4 alpha cubed. And finally, we have I3, which is equal to 3 over 2 alpha I2, which gives us 3 over 8 alpha to the 4th. All right, so now we can hopefully toss these integrals away and not have to worry about those again. All right, we'll be seeing these integrals throughout this, and it's nice to have them all done beforehand. All right, so first thing we need to do is normalize our trial wave function. So we're just going to solve for A. So we can do this here on the first page. So what we have here, we're just going to use the basically psi star psi, right? It has to be equal to 1. All right, normalization condition. All right, so this wave function only exists from 0 to infinity. 0 to infinity, we get the absolute value of a squared, and we get an x squared e to the minus 2 alpha x dx equal to 1. All right, now if we did our integrations right, this should be equal to I2. This right here, of course, with this constant a out front. So what this is this, sorry, a norm squared, is just this absolute value of a squared, and then I2. So we just come here, look it up. We've already done it. 1 over 4 alpha 3 equals 1. So this tells us that a is equal to, so we have, when we bring this up here, we get 4 alpha cubed, and then take the square root, we get 2 alpha to the 3 halves. So our normalized wave function is equal to 2 alpha to the 3 halves, and then right up here we see it's an x e to the minus alpha x. This is our normalized wave function. All right. Okay, so now we're going to obtain the expectation value of the kinetic energy. All right, so just calling this a generic C, I guess. All right, so to do this, first let's just look at T real quick. T is just the kinetic energy, P squared over 2m, which when we put in the operator for P, we get a minus from the i's, we get an h bar squared over 2m, and then two derivatives with respect to x. Okay, so this expectation value here, we'll just be integrating from 0 to infinity. We will have, I'm going to bring the constants out front, so our normalization constant we found. We'll square that. We get a 4 alpha cubed. Okay. All right. And then we get, so we get an x e to the minus alpha x. Oh, and I should have also brought out our minus h bar squared here, and 2m. Okay, it's getting kind of jumbled in here. There's an x e to the minus a, or alpha x here. And then we've got our double derivative with respect to x of, again, x e to the minus alpha x. All right, so this is our expectation value for the kinetic energy. So let's finally bring out the constants for real. So we have this 2 and this 4 is going to kill each other. And we have this minus sign here. So we have an alpha 3, we have an h bar squared, and we have an m. All right, and then here get our integration x e to the minus alpha x. All right, let's do these derivatives one at a time. So here we would get, taking the derivative, we've got the first part, so we just get e to the minus alpha x plus x, and then a minus alpha here, e to the minus alpha x. Okay, so just the product rule. Great. Minus 2 alpha cubed h bar squared over m. And let's go ahead and take these other derivatives here. So we'll bring down a minus alpha for this first derivative here, e to the minus alpha x. All right, and then we have minus alpha multiplied just by what we, anyway, what's left over is just this x e to the minus alpha x, which is what we had up here. So we just get the same thing that's in these parentheses here. So e to the minus alpha x. I'll go ahead and bring out this minus sign, minus alpha x e to the minus alpha x. Okay, all right, and then we have this other parentheses here. All right, here we go. Continuing on, finding the expectation value of our kinetic energy. We've got a minus 2 alpha cubed h bar squared over m. Now let's see if we can make any sense of this. How should we do this? Let's just multiply these two terms together. So we get a minus alpha x e to the minus 2 alpha x. All right. And now we will multiply this and then these, this term right here. So we have a minus alpha x. There's minus alpha x, and then e to the minus 2 alpha x again. Okay. And now we get our final term, which is this multiplied by this minus alpha multiplied by this last term. So we'll come down to this second line here. We get a plus. Okay, we have an alpha squared, we have an x squared, and then our e to the minus 2 alpha x. All right, dx. All right, so let's go ahead and see what we can do here. So we have a minus 2 alpha cubed h bar squared over m. We are now going to bring out the brackets, bring out the braces, the brackets. We get two integrals that are the same. So we have a minus 2 alpha, okay, and then we'll have the integral of just x, so 0 to infinity x e to the minus 2 alpha x, which we have already done, which we are calling I1. All right, and then we have plus alpha squared right here, and then doing this, the integral of this term here, we can see an x squared e to the minus 2 alpha x. This is our I2. And here we go. So now we just plug in what we've got. I can go find it, dig it back up. Equals minus 2 alpha cubed h bar squared over m. And then we have our I1 here. So we get a, this, where am I? So this minus 2, so we'll still have a minus sign here. We're going to get a 1/2. Yeah. 1/2, and then 1 power of alpha here on the bottom. All right, plus alpha squared times I2, which is just 1 over 4 alpha. All right. Okay, so this obviously comes out to be a minus 1 over 4 alpha, leaving us for, again, for the expectation value of the kinetic energy. This leaves us with, this minus sign is going to go away. This 4 is going to kill the 2. And we'll have an a squared, h bar squared, 2 on the bottom, and an m. All right. I hope I got all that right. I think I did. All right. So let's now move on to the expectation value of the potential, or potential energy. Okay. We'll go back and find our normalized wave function way back here. Here we go. All right, so we're just doing the same thing, except there's a potential in here, like so. So our potential is just kx. So nothing too fancy. Here we're integrating from 0 to infinity. Let's go ahead and bring out some constants again. So we have our 4 alpha cubed. Then we have an x e to the minus alpha x. Okay, our potential was just kx, and then x e to the minus alpha x again. Excuse me. Dx. Now, let me switch to a blue marker so it'll be a little bit darker. Now, nothing fancy going on with this operator. We don't have to take any derivatives this time. So we have a 4 alpha cubed. We have this k, or kappa, whatever we decided it was. And then we have 3 x's, so we have an x3 e to the minus 2 alpha x dx, which is just equal to, bringing the constants out, 4 alpha cubed k, and then what's left is our integral with the x cubed inside, which is an I3. So again, going back to our little cheat sheet, we get, so we'll have, let's just write these all out and cancel things. So 4 alpha cubed k, and then a 3 over 8 alpha to the 4th. Okay. All right, so alpha cubed will cancel with all but one of the alphas. and this 4 is going to turn this down to 2. So we end up with we have a 3k on top and a 2 alpha on the bottom. All right. So now, our expectation value for the total energy will just be our expectation value for the kinetic added to the expectation value for the potential. So let's just write that out real quick. Okay. So let's go back and find our, so I think here's where we finally settled on an expectation value for the kinetic. And for our potential energy, we had this. All right. So we are going to minimize this. Just double check, make sure this matches up with what I found earlier. All right, looks like everything checks out. Okay, so we're going to take the derivative with respect to our variational parameter alpha, set that equal to 0, and there's no, just guessing by the shape of this potential, we're not going to end up with a maximum of the energy. So we'll assume that when we won't have to try and decide whether we've got a minimum or a maximum. We'll just assume it's a minimum. And away we go. So let me just call this E. Okay. All right. So the derivative of, just make sure, yeah, do the total derivative with respect to alpha. Okay. All right, so what we get is a 2 alpha, which will cancel with this 2, so we just get an alpha h bar squared over m. All right, and then this alpha is alpha to the minus 1. We get a minus 3 halves k, and then on the bottom is an alpha squared now. And we're setting this equal to 0 and solving for alpha. So this tells us, let's go ahead and, well, all right, we'll just write it out real quick. So alpha h bar squared over m is equal to 3 halves k over alpha squared. Bringing this alpha up here, we get an alpha cubed on this side, equals, we'll have our 3 halves. From here, we have a k. We're going to multiply by both sides by m and divide by h bar squared. So this tells us that alpha is equal to this 3 halves k m over h bar squared to the 1/3 power. All right. So this is the alpha that gives us the minimum energy. So the last thing we want to do is find out what that minimum energy is. All right, so where we go. Let's see. Our energy was just this right here. So I'll just call this E min. Okay. Alpha squared h bar squared over 2m plus 3k over 2 alpha, where alpha is equal to this 3 halves k km over h bar squared to the 1/3 power. All right, so let's just plug and chug real quick. I get an h bar squared over 2m, and then this 3/2 km over h bar squared to the 2/3 plus a 3 k over 2, and then an alpha, or this 3/2 km over h bar squared to the minus 1/3. Is there any way to make this pretty? Let's see. Alright, so it looks like a good way to do this is actually to factor out a 2 h bar squared over 3 km to the 1/3, which if I didn't have this minus sign up here and had it flipped, that's what that would be. So then what we end up with from this term, we have the h bar squared, we have a 2m, and then we just have what's inside here. So 3 km over 2 h bar squared, and then this part got factored out, so we just have a plus 3k over 2. Alright, so in here we get our h bar squares to cancel, our m's to cancel, and this piece here is just a 3k over 4. Alright, so this part here will be a 9k over 4, giving us, a 6k over 4, giving us a total of 9k over 4 for the inside piece here. So then if we write that, so we have a 2 h bar squared over 3 km, this is to the 1/3. And then we write this as a 3 squared, or 3 to the 6/3, over 2 squared, or 2 to the 6/3, and then a k to the 3/3. Okay. Then this 2 to the 1/3 power is going to cancel with one of those 1/3 powers of 2. And this 3 is going to cancel with one of those. And then this k on the bottom to the 1/3 will leave a k to the 2/3 up top, and then we're going to bring that in here. So what we get is this k comes here as a k squared h bar squared over m to the 1/3 power. And then left over from this, we have a 3 to the 5/3 over 2 to the 5/3. So there we go. All right, so I don't know if this is actually the ground state wave function or not. Sometimes with these variational principle problems, particularly if what is it? Anyway, with the Gaussian or whatever, sometimes you happen to stumble upon like the actual ground state. So I don't know if that's the case, but this energy here that we minimized. All right, so the actual energy of the ground state is going to be less than or equal to this energy that we found. So we found an upper bound for the ground state energy of this sort of ramp potential up against an infinite wall. So whatever the real ground state energy is for this, it's got to be less than this number.